So lesson number 2 looks at trig ratios on a calculator and patterns in trig ratios. Oops, wrong way. There we go. So if you recall from what we did in the last class, the SOHCAHTOA, that was looking at our primary trig ratios and the relationships that happen. So what this means is if I measure the opposite side to the hypotenuse of a 35-degree angled triangle, it doesn't matter if this triangle is a little one or if it's a great big one. The opposite over the hypotenuse gave me the same ratio each time. And we did the same thing with our 58-degree angle. That's how we started off yesterday's class, was taking those measurements of those triangles. So there are 3 such relationships, these 3 primary trig ratios. Opposite over hypotenuse for sine, adjacent over hypotenuse for cos, and opposite over adjacent for tangent. Now, we can use our calculators to help us figure out these tan ratios. If you grab your calculator right now, make sure, so turn your calculators on. Press the mode button on your calculator and make sure that degree is highlighted in black. If it is not, you would scroll down to, so let's say this is what my calculator looked like. Was the radian was highlighted, I would scroll down over to degree and press enter, and then it would highlight degree. My calculator needs to be in degree mode because that's what we're calculating. We're calculating degreed angles. When we get into grade 12, we'll look at radian measurements, but for now we're looking at degrees. So if I typed in tan 35, I get 0.700207538.2, and it probably goes on after that. This is the specific ratio of the opposite side to the hypotenuse, using far more precise measuring tools than we have access to. So what we had access to gave us the 0.7. So to 4 decimal places, I would write that down as 0.7002. And then if I had to do tan 38, or sorry, was it tan 38? Yeah. If I had to do tan 58, 1.600 and on. So that's very close to the answer that we got in the last section of 1.6. So to the nearest 4 decimal places would be 1.6003. So, I'm going to give you a moment. I want you to do class example 1A. Determine the value of each trig ratio to 4 decimal places. So to 4 decimal places, what is sine 35? 0.5 what? 736. Thank you. Cos 35.
0.8192.
Sine 58.
0.8480.
Thank you, Taylor. Cos 58.
0.5299.
Thank you, Helena. So with respects to the diagrams at the top of the page, what ratios of the sides is represented by each of these ratios here? So what that's asking is sine 35, if I go up to the top of the page, sine 35 is side AB over OB, opposite over hypotenuse. So AB over OB. So take a moment to write down what the ratios would be for the other 3 trigs. Okay, so what is sine 58? What 2 sides are being compared in sine 58? what's the opposite side called? AB. What's the hypotenuse called? OB. If I look at cos 35, so that's in the first diagram, what's the adjacent side called? OA. And the hypotenuse was OB. And in not sine, cos 58, the adjacent side was OA, and the hypotenuse again was OB. So when we talk about cos 58 being 0.5299, what we mean is if we take the adjacent side length and divide it by the hypotenuse side length, we'll get this 0.5299. That's what that means. So let's say we drew true triangles. One had an angle of 35 degrees, one has an angle of 58 degrees. And we set the hypotenuse to be equal to 1 in both of them. As this angle here went from 35 degrees to 58 degrees, so as it increased, explain using SOHCAHTOA why the sine value, so the ratio of the sine would increase, but the ratio of the cosine would decrease, and then determine what happens to tan. So let's start one at a time. Let's start with sine. And we'll call it sine of angle O. Sine of angle O is equal to the opposite side over the hypotenuse. That's AB over 1. That's what the sine of angle O equals. And if we call this diagram 1, and this one diagram 2, what happens to the length of AB in the second diagram? It increases. So side AB increases from diagram 1 to diagram 2. If that side length increases, it means that the ratio would then increase. So then if we looked at cos of angle O is the adjacent side over the hypotenuse. Well, as I go from the first diagram to the second diagram, what happens to the side length OA? It gets smaller. So side OA decreases. So the ratio would decrease. In other words, as my angle gets larger, my opposite side will get longer. And as my angle increases, my adjacent side becomes shorter. And you can try that. If I took a triangle, so if I take a triangle, and we'll just put this like that. If I take this and this becomes my angle, as my angle increases, look what's happening to my opposite side. My opposite side is decreasing. That's what's happening. So it's virtually impossible to be able to get this to start to become shorter. My angle, my opposite angle, just keeps getting bigger and bigger. If I was to fix this and I was to change, try and figure out how the best way to show you that this angle gets shorter.
I'm doing the area. For the area, I'm not.
I think it would be if I went,
But I thought we were gonna find like.
if I make this angle greater, look at what happens. So this is a greater angle than this angle. Look what's happening to my line. My line is getting shorter.
The volume.
So as this angle here increases, my adjacent side becomes shorter. As this angle increases, my opposite side becomes longer. Do you see that? Does that help with the visual? Okay. So then, if I think about tan, as my tan, what is tan? Tan red here. Tan of angle O is the opposite side, which is AB, over the adjacent side, which is OA. Now, as my angle increases, AB is increasing, and OA is decreasing. So what's going to happen to my tangent ratio as my angle gets bigger? My tangent ratio is going to become larger. So the tangent ratio will increase. So in class example number 3, without using a calculator, state which of the following ratio as the greater value. So which is going to be greater, sine 14 or sine 20? So think of my angle. If this is my triangle, if I'm going from 14 degrees to 20 degrees, is my opposite side getting longer or shorter? Longer. So sine is going to get bigger. So cos, if I was going from 7 degrees to 62 degrees, is my adjacent side, what's going to happen to my adjacent side? So maybe it's better to go 7 degrees to 62 degrees. What happens to my adjacent side? It gets shorter. So then cos 7 is going to be bigger than cos 62. And in the tangent one, the tangent relates to sine. So it has sine increases, tan increases. So tan 75 becomes bigger than tan 15.
What's the diameter of 20? No. The diameter of 20.
Now if I look at D,
Oh, yeah, I'm doing the volume.
which is going to be the biggest of these three? The sine, the cos, or the tan? Well, we should hopefully know that cos is going to be the smallest one, because cos 80 degrees, if I think of the triangle that I have to draw for it, 80 degrees is a pretty steep line. So this is going to be a pretty short adjacent side. So cos I can eliminate. Now, what do I know about sine? I know that this side always has to be shorter than my hypotenuse, which means that this value here is going to be less than 1. But with tan, I have an opposite side and an adjacent. When I take this side length and I divide it by this side length, my answer is going to be greater than 1, isn't it? Just even if by looking at this simple sketch. This is going to be more than 1. So that's the higher ratio. Okay, so do class example number 4. So if we look at class example number 4, what is sine 81 to 4 decimal places?
0.
What is tan 14?
0.2493.
And cos 44?
0.719.
93. Oh, thank you. So the purpose of this is just to understand, or to kind of, because we always talk about estimation and estimating, is to understand that if I type in sine 81 and I press enter, I should be getting a number close to 1. Because this is a high number, this should be a high ratio value. And the same thing with my cos. If my cos is a low number, it should have a larger value. Because let's say, for example, by accident, somebody played with my calculator and put it into radian mode. So I had tan 58, or let's start with sine 81. If I type in sine 81 now, I get this negative 0.629. Even if it wasn't a negative, this answer here is off. And I should hopefully be able to recognize that even if I ignore the negative and I look at the 0.629, that's not possible. Because again, my 81-degree triangle is a fairly steep triangle to get this 81 degrees. Which means these two measurements here are going to be close to being the same. This number is going to be close to 1. So that's the purpose behind investigating this, is just to understand what happens to the values as I move from a small angle to a large angle. So it says, we have discovered that tan 35 is 0.7 and tan 58 is 1.6. But is there an angle for which tangent is 1.2? So if we did a guess and check, we know that tan 35 is 0.7. So tan 35 is 0.7 and tan 58 is 1.6. So let's try tan. Kind of almost need to be almost right in the middle, right? So what's halfway between 35 and 58? Like 45. What's tan 45? 1. Okay. So now I'm between tan 45 and tan 58. Try tan 50. What do I get for tan 50? 1.9? 1.19. That's pretty close. So try tan 51. What do you get? So it's got to now be somewhere between tan 50 and tan 51. So what if I try tan 50.5? What would I get? 2130. So now I'm kind of between these two. So maybe I now try tan 50.4. What's 50.4? What did you get, Delana, for tan 50.4? 208?
Yep.
So let's try one more. Let's try tan 50.3. What do I get for tan 50.3? Kate, what did you get for tan 50.3?
1.204.
So I'm getting closer. And then that's only to the nearest 10. Then I could like go through the whole process again for the nearest 100. Pretty time consuming, and it's actually kind of pretty messy on the page, isn't it? So what if we could figure out what the angle was using our calculator? That's this inverse process. So to get the ratio, So to figure out what the ratio is between the opposite side and the adjacent from a given angle, let's say it was tan 35. So I need to get back into my right mode. When I press tan 35, I get 0.7002, etc., etc., etc. That gives me the ratio between that angle. But what if I knew the ratio and I wanted to get the angle? Well, then I work backwards, and that's an inverse operation. It's the same as squaring and square rooting, multiplying and dividing, adding and subtracting. So if I wanted to work backwards, I'd go second inverse, and if I type in this ratio, let's say I brought it just even to 4 decimal places, there's my 34.99997, which when I round it becomes 35. So, if I have sine A equals 0.3584, to get to angle A, I would sine inverse it, 0.3584, and to the nearest degree would be 21. So do the same for the next 3. Okay, what is angle B for in B? How much? 57. And angle P? 73. Angle C? Good. So I think we'll do some practice questions. So question number 1, parts A, D, G, and I. Question number 2, parts A, C, and E. And question number 3, let's do A, C, E, and G. And then for question number 4, would be A, C, E, G, and I. So every second one. So although it's not possible to form a triangle where angle O, so if I was to draw a triangle, I can't draw a triangle where this is 0 degrees, nor can I draw a triangle where it's 90 degrees. It still is actually possible to calculate the trig ratios for these angles using the idea of rotation. So if I look at a rotation angle of angle A, is formed when a length of R is rotated counterclockwise. So we rotate counterclockwise because we have to think about being on a coordinate grid. This is our home part, is when we're right along this positive x-axis and we rotate in this direction. So if I take this rotation angle and I rotate it, I get triangle AOB as shown in this diagram. So this would be AOB, and my sine ratio would be the opposite, which I can call Y over R. And the reason why it's Y is, again, if I go back to my coordinate grid, if I draw a triangle on this coordinate, the height of my triangle corresponds to the Y coordinate, the length of my triangle here corresponds to the X coordinate. And the reason why we have this value of R is if I keep drawing or keep going around, I would get a circle, and R would be my radius. So Y would, or sine A would equal Y over R. So then cos A, adjacent over hypotenuse, would be X over R. And tan, which is opposite over adjacent, would be what letters? Y over X. Good. So if the rotation angle of A is made smaller, so if I make this smaller, what ends up happening is the opposite side, my y value becomes smaller and my x value becomes larger. So if the side, or if A is equal to 0, then my opposite side would be equal to 0, because that's how I would get kind of that 0 triangle, is my value of y would be equal to 0. So in these trig functions, if y is equal to 0, this would equal 0. And this would equal 0, because y is equal to 0 in each of those. And cos, well again, if I think of this triangle, if I drop it down to 0 degrees, my r value is going to be the same as my x value. So instead of writing this as x, I can put it as r over r. And if I take something and divide it by itself, I get 1. And you could double check this on your calculator. You could go sine 0 equals cos 0 equals tan 0 equals. Now let's suppose we made this A value larger and larger until we got to 90 degrees. So if we could make my angle 90 degrees, my x value would be equal to what? There would be no x value. Like that would be taking this angle, if I make this 90 degrees. There's my y, which now is going to be the same as my r. And my x value is nothing. So when I look at that 90-degree angle, my x value is nothing, so this becomes 0. My y value is the same as my r, so I get that sine 90 equals 1, cos 90 equals 0, and then when I get into tan, I'm going to have this y value, which was my r, over 0. Can I divide by 0? What happens if you try to divide by 0 on your calculator? What do you get, Taylor?
This is error.
It says error. I can't divide by 0. This is not possible. So what we don't say it's not possible, what we say is undefined. Senior high mathematics does not give us the tools to divide by 0. And that's because at this point, every time we divide, we're talking about dividing something into groups. How do I divide something into no groups? Doesn't really make sense. There has to be at least one group, the whole thing itself. I can't divide it into 0 groups. There has to be something to divide it into. So if we complete the following table, I know that sine 0 was equal to 0, right? Is that what we just did before? Yeah, sine 0 was equal to 0, and sine 90 was equal to 1. I want you to fill in the rest of the chart to 2 decimal places. So sine 10 equals, sine 20 equals, sine 30 equals. So let's fill this in. 10 degrees, I get 0.17, 0.34, 0.5, 0.64, 0.77, 87, 94, and 98 hundredths. So as the angle goes from 0 to 90, sine x increases from 0 to what? So if we look at triangle LMN, I want to draw a triangle LMN where angle L is equal to 90 degrees and angle N is equal to x. So L has to be right here, and M and N, it doesn't matter which one I put where, as long as I label this as being x. N is x, what would angle M be? So let me repeat that. If angle N was x degrees, what would angle M be? So let's pick a number. If angle x was 12 degrees, what would angle M be? What'd you get, Delana?
78.
And how'd you get 78?
180 degrees, subtract 90 plus 12.
So you're subtracting 90 and then really you're taking off another 12, right?
Yeah.
So if I change this to, let's make a number that we can work with, 20 degrees. I would do the same thing. I take 180, take the 90 off. Well, if I take 90 off every single time, because I know I have 90, what am I left with? 90. So if I take another 20 off 90, I'm left with 70. If this was 35 degrees, if I take 35 degrees off of 90, I'm left with 55, and so on. So what did I do? I took 90 degrees, and I took off whatever that measurement of x was that I was given. I just don't know what x is. So I can say that angle M equals 90 minus x. So then it says, explain using ratios why sine x would equal cos 90 minus x. Well, sine x equals opposite over hypotenuse, which in my triangle, the opposite side is ML, and the hypotenuse is what? MN. So now if I go to my cos 90 minus x angle, so my 90 minus x is this one right here. 90 minus x degrees. Well, cos is adjacent over hypotenuse. What's the adjacent side of this triangle called? From this angle, what's the adjacent side? ML. From this angle, what's the hypotenuse? MN. They're the same. I've just shown why sine x would equal cos 90 minus x. So, if I give you sine 20, what would sine 20 be equal to? So sine 20 would equal cos. So 90 subtract x, which is 20. What's 90 minus 20? 70. So cos 70. Sine 8 would equal cos what?
90 subtract 8.
And what's 90 minus 8? 82, yep. And I can check this. Sine 20 cos 70. Sine 8 cos 82. So if for perhaps on a quiz I said that the cos button was broken on my calculator and all I could use was the sine and I wanted to find the cos of a 63-degree angle and all I could use was sine, what would I have to type in? Sine what? What would I type in, Taylor?
Sine 90 minus
90 minus 63? 27. Good. Okay, before I give you the questions, I want to skip to a question. I want to skip to question number 5. Explain using diagrams why the sine ratio for an angle of 20 degrees is smaller than the sine ratio for an angle of 40 degrees. The sine of an angle is what ratio? Opposite over hypotenuse. Okay. So if I have a triangle that has a 20-degree angle, and I increase that triangle to be a 40-degree angle, what have I done to the opposite side? Yeah. As you move from 20 degrees to 40 degrees, the opposite side gets longer. So the ratio would increase. So I guess because we're supposed to be going from 40 to 20, it would be going the opposite way. As you go from 40 to 20, the opposite side gets smaller. So the ratio would then decrease. So the reason why I did question number 5 with you is because I'm giving you question number 6 and 7 to do for explanations, and then 12, 13, and 14.